Thank you very much. I really appreciate the opportunity to be able to give a talk. And before I want to start my talk, I really want to thank all the organizers as well as the previous and upcoming speakers for really making this webinar series possible. I think it's a fantastic idea, not only because of the quality of the content that is available, but it's bringing us together, all these different communities, and helping us develop, a common language to speak amongst each other. And a little bit of an inspiration of, kind of appeal to this broader community. One thing I wanted to show today is how can you deliver specificity when you try to do label-free imaging. And I'm going to split my talk into two sections, kind of to cover the majority of the community here. One is related to the sensing community, and another one to the photothermal. For historical reasons, I'll start for the context of sensing because I come from a background of iSCAT microscopy. And so I always like to start the talks by saying, what is the final goal? Or why do we do this, right? And so when we do sensing, the type of research we want to do is to really temporally quantify analytes in a complex matrix. And this is quite nicely, shown here in the schematic. And the reason why we do this is that if you choose your analytes correctly or appropriately, you can turn them into this key word called marker. And all this simply means is that if you can follow and count these individual markers, they will report on the specific state of the system. And this can be a physical system, it can be a biological system, and it can be a chemical system. And also, because life is dynamic, we want to be able to get time-resolved information. So we want to see how these markers are changing the concentration over time, and not only see one marker, but multiple of them. And so how do we go about doing this? So throughout the years and working in the group of Roman, we put together lots of different tools together, and we call this our interdisciplinary toolbox. So here we combine photonics with computer vision, as well with surface chemistry and microfluidics. Since this webinar series is more focused on photonics, I'll talk a little bit about the microscopy side. And so for our choice of microscopy, we like to do label-free imaging, because this means that when we have complex samples, we don't have to modify them at all. And for our choice of label-free imaging, we're going to work with elastic scattering. Yeah. So the price that you pay when you work with label-free based on elastic scattering is that this is rarely specific. So everything scatters. So you have to work really hard to deliver specificity, especially when you work with complex biological samples or very heterogeneous ones. Because most often than not, you don't know what's inside this complex matrix other than it must contain some of your analytes of interest. So they come in different sizes, different material properties. And also, if you work with biological material, most often than not, the way how to differentiate between the things that you're interested in is to rely on biological functionality. So telling apart two proteins that have similar size but different functionality. So that's our challenge. So in the group, we develop different types of platforms that address specificity in different ways. We can use biochemical means, and this is what I'm going to focus on today, at least in the first half of the talk. And this is by developing immunoaffinity pull-down assays, by using nature's own capture probes, which are antibodies. But we've also developed physics-based approaches that combine information on scattered light as well as their size. And this has recently been published in work in collaboration with Mats Liebel. Or you can also work with spectroscopic means, which we've seen throughout this webinar series, either using Raman or mid-infrared photothermal spectroscopy. So specifically in this talk, I want to focus on how to deliver biochemical specificity. And the way how we do this in the application we have in mind is to develop a molecular fingerprint so that whenever we look at a heterogeneous sample, we look at the different types of markers to develop this fingerprint, the specific fingerprint. So in the context of biology, this is normally done, and this is represented by these kind of proteomic data. And there's a lot to digest here, but I just want to draw your attention to the x-axis. All these acronyms really represent your markers. So these are, specific proteins. The different intensities really represent how much of that protein and how much of that marker is in my sample. And then along the y-axis are my different types of samples. So as you can see, given the different types of intensities for each marker, you can identify that you can generate a unique barcode for each one of these different types of, in this case, cell lines. The main analogy for this, because this audience is mostly has experience with spectroscopy, is just to think of this biological fingerprint as, rather than you just convert the word marker into a vibrational mode. So you can just think of this as doing a SIRS measurement, doing a Raman, doing mid-infrared photothermal spectroscopy. So this is exactly the same thing, we just go about it in different ways. So in order to develop this platform, we need to satisfy basically 4 basic requirements. We have to develop sensitivity, we need to develop throughput, also give specificity, and also deliver multiplexing so that we can see different markers. And so in order to develop sensitivity, it's needless to say that I don't really have to talk much about this, because throughout this webinar series, we've seen amazing work from different types of groups, all covering different types of holographies. So if in case of ISCAT, you have the talks of Vahid, Philip, Naomi Ginsberg, Kobri, you have Chia-Lung Xie, and the list goes on and on. So I really encourage you to look at these different speakers in the YouTube channels that we available in the webinar series. So the next item on my list is, how do I deliver throughput? And by throughput, I basically want to be able to image as big a field as possible so that I can collect as much statistics as I want. And if I'm going to use microfluidics channels, microfluidic systems, I basically want to be able to capture all the information inside my sensing area. And so, this should be relatively straightforward. So you pick one of the holography methods. So you can pick ISCAT, and you get your microfluidic chip, and you simply, do a color illumination, and therefore you have wide field illumination. And therefore, you're good. However, if you do this experimentally, you'll get a horrible, horrible looking image that looks like this. And this probably explains why ISCAT took a long time to be adopted through different communities, because most of them work with fairly heterogeneous samples, right? So you work with a flow cell microfluidic chip with lots of things, lots of particles in the middle. So you have multiple scattering, multiple interfaces. And if you're working with coherent light illumination, all of these lead to coherent artifacts, either in the form of speckle patterns or in the form of parasitic interferences. And so this coherent artifacts is not something new. This has been reported back from the 60s. It only took about 50 years for a group by Young Park to really do a very methodological study to see which way can you most efficiently reduce the coherent artifacts. And in this graph, you basically want to highlight that there's 2 ways to reduce the coherence artifacts. You can either decrease the temporal coherence, or you can decrease your spatial coherence. And for starters, when I began my measurements, so with this wide field ISCAT, you're basically situated in the top left corner. So the worst possible scenario, where you get mostly a lot of contamination from speckle noise. So if you look at this plot, the best way to improve your imaging quality would be to reduce your spatial coherence. And you can think about how to do this by just increasing the spectral bandwidth in your spatial domain. And this means coming in illumination at different angles. And there's been several implementations of this throughout the years. So you can do this by scanning your beam using AODs. You can also implement confocal scanning ISCAT or spinning disk confocal. And these are topics that were covered in the previous seminars by Vahid and Chia-Lung. So I would like people to refer to that. But if you want to do sensing and you want to cover a big field of view, you basically want an approach that you can do this in a very quick manner and also subject your sample to low peak intensities. And you might think this is actually difficult, but in fact, this is actually quite straightforward. If you have a microscopy setup that is based on a single mode fiber coupled laser system, if you switch your single mode fiber for a multi-mode fiber coupled LED, suddenly the same exact image becomes actually workable. And so you might raise the issue, well, okay, if I work with an LED, my power is going to drop a lot, so I might suffer from the sensitivity. Well, actually, you can turn your laser into a spatially incoherent one by just, coupling your laser and passing it through a rotating diffuser. And you can get the same, quality of image as before, as with an LED. So the big question comes now is actually, can you optimize your signal to noise ratio by carefully choosing the degree of spatial coherence? And this is where a PhD student, Chiara, comes into play. So she worked with a sample with different types of particles, and she tuned the spatial coherence by varying the illumination in A. And what you see here is that as you increase the NA of illumination, what you're doing is decreasing the spatial coherence. And as a consequence, not only are you decreasing the effect of speckle, but you're also slightly decreasing the interference contrast. So the best way to see where to evaluate your sensitivity and how much you gain is to characterize the signal to noise ratio for each one of these different particles. And it turns out that there's a sweet Goldilocks signal to noise regime that is not too short of a coherence length and not too long. And you can actually gain almost a factor of 2 in signal to noise ratio by just tuning the NA of illumination that you can work with. So now that I know that you can illuminate a big field of view, the question is, how big can you make it? And it turns out that this is actually space bandwidth product limited. And in our case, this was mostly limited by the size of our available detectors. So at the moment, we were eliminating a field about 130 microns field of view with an objective of 1.46. And if we wanted to get a bigger field of view, so increase our throughput, what we simply had to do is to stitch multiple images together. And this is kind of a well-established technique in the field of microscopy. You can continue pushing this to cover the whole sensing region of a microfluidic chip. And this is exactly what you can cover up to millimeters of field of view just by stitching multiple images together. And so this, again, if for the people that are interested in sensing, you might raise the question of, does this lower radiance impact the sensitivity? Do you sacrifice, your signal to noise ratio overall? And you can compare the state of the arts of how much of a sensitivity you can achieve. This is from work from Vahid from 2 years ago, well, 1 year ago, and you can reach about 10 to the minus 4 sensitivity in about a second or so. If you use an LED, you have roughly an irradiance that's 1,000 times lower, but if your system is still shot noise, it doesn't matter, right? As long as you collect enough photons, it's only going to take you 30 to 40 times longer to reach the same level of sensitivity. And this is exactly what happens, so this shouldn't come to a surprise. The more surprising thing is that the system seems to be remaining stable after a minute. This has to do hand in hand that, we've eliminated a lot of the speckle contributions that, deteriorated the noise in this aspect. So that is all I want to say about throughput. So now let's go into the next aspect. How do we deliver specificity? And for this, we're just going to use the nature's own capture probes, which is the antibodies. And so for those that do sensing, it's not sufficient to just have your antibodies that recognize a specific analyte of interest. You also need to add a passivating layer. And the role of this passivator layer is to really prevent other molecules that are not of interest from binding to your surface. And so not only there's that requirement, since we're working with a label-free imaging technique, and we're also working with microfluidics, you have to make sure that all of the surface functionalization is compatible with your imaging and with your microfluidics. And it turns out that a very nice strategy, a system that works well, is something, my very first system that I worked with during my PhD, which is a supported lipid bilayer. So just put a lipid coating as your building block. There's some challenges with working with lipid bilayers, and then in the sense that they're not always clean, there's always a little bit of defects. But if you work hard enough, this is the work through the thesis of a PhD student recently graduated, Alexia. She found a protocol where you can, do a repair-mediated formation of supported lipid bilayers. And I'll just let the image speak for itself, right? So this is a scan over 1 millimeter by 200 microns. And you can see that the amount of defects that are in this bilayer are very, very small. And you can quantify it, and this is on average of 1 defect per 200 microns squared. So this is actually a very good starting point to build our immunoassay. So we can then add the next parts of the functionalization scheme. So we add our antibodies. So now we have our kind of immunoassay. So now we have to validate it. And the first step to do that is to run the positive and negative controls. And so positive just simply means that the analyte is actually is recognized by your capture probes, and negative means that it shouldn't be recognized by your antibody or capture probe. And it turns out that the immunoaffinity assay passed this test. A more stringent test is to do a dose response. So you get your analyte of interest, you vary the concentration, and you would hope that you have a linear response followed by a saturation of your sensor. And this is exactly what happened. And so hopefully with this, I've been able to convince you that through the surface chemistry, we've been able to turn the substrate into a sensor that we can now use to pull down our analytes or markers of interest. What is missing is a biological system to test this out, right? And so this is where, a very fruitful collaboration started with Professor Hako Lee and Hyung-Soo Im from the Harvard MGH unit, and they introduced us to the world of extracellular vesicles. And all you need to think about them is these are nature's equivalent of a biological nanoparticle. Most cells are secreting this on a daily basis, and they come as heterogeneous as you can think of. They are both physically, chemically, and biologically heterogeneous. And the main significance for them in the community is that they are a liquid biopsy systems. That is, that they contain information from the cell that which they originated from. From our perspective, they're actually a great system to work with because this biological nanoparticle composed of a lipid bilayer is surrounded by proteins that are embedded on the surface, which you can target specifically using our immunoassay. And from this, we would hope to test our fingerprinting abilities. So the first thing we did is we targeted a surface marker that is ubiquitously expressed in most of these EVs, which is called CD81. And we used a microfluidic chip where we can basically change different concentrations all within the same system. And what we saw is that within the dose response, we can actually follow the binding kinetics for each of these different concentrations over time. And so again, I've started to come closer to my goal to temporally quantify different analytes within the system, right? So this seems to validate that, my immunoassay works. So now the next step is, where does the fingerprinting come in? So now all I have to add is the different markers. So I'm going to investigate different markers for my EVs. And this simply means I'm going to target different surface proteins. And here we let the collaborators choose the different relevant proteins that are ubiquitous for the EVs and those that are relevant for cancer, because these EVs were derived from cancer cells. And all you do is you couple them all into a same chip, functionalize each different sensing channel with a different capture probe, and what you get is the binding kinetic curves for the different EVs. And from these binding kinetic curves, you basically count the number of EVs that express that particular surface marker, and in a way, you've generated the protein expression levels for each of these different markers for the population in EVs. And this is exactly the start and the makeup of our molecular fingerprint. Yeah. So now to test this is let's see whether if we change the source of different nanoparticles, so changing different cell lines, this fingerprint allows you to discriminate between one another. And hopefully in this curve that you see here, we have the different markers for the different cell lines. And if you quickly inspect by eye, you see that there are subtle differences between them. So this allows you to start to develop a barcode. And this is very analogous to what I started with the proteomic data. The only difference is that as our markers, we only pick 6. So these are the different columns. And as the rows, we just have 4 different cells. The main important difference here is that we're working at the single particle level, the single EVs, and whereas the other one is looking at the ensemble and looking at the whole cells as itself. So it's a step in the right direction. Okay, so extracellular vesicles are rather big, so they come in sizes from 30 nanometers up to a micron. So the question is, well, can you apply this system to discriminate proteins? So can you do secretion-based studies? And the answer to that question is yes. You can actually look at proteins in your microfluidic chip. So here you can just add in fibronectin through the chips, and you're actually pulling them down using this immunoaffinity assay. So here the quality doesn't look so good because I'm only using the first image as a background to correct for the surface roughness. But since I know my microscope is stable for up to a minute, I can update the background every 20 seconds, and I can really increase my signal to noise ratio appropriately. So now I can study the antibody-antigen interactions and more generally, particle-particle interactions. And hopefully with this, I've convinced you that you can deliver specificity to label-free imaging techniques using biochemical means. So for the other parts of the community, so what about photothermal? How do you deliver specificity there? And again, I want to start by motivating and outlining what is the goal here of our research line. And that is to spatially, temporally quantify temperature and its effects on the surroundings at the microscale. And the very first component of delivering this goal comes down to how do you measure temperature at the microscale? And for this, we like to, again, use label-free approaches. And I don't have to work too hard about this because Guillaume has very nicely explained that you can use wavefront-based thermometry to achieve this. And the way how this works is that if you generate a thermal gradient at the microscale, if you impinge light on it, this thermal gradient will cause a distortion on the wavefront, which you can measure if you have a phase-sensitive microscopy imaging technique. And the very first microscopy imaging technique that worked with this for this thermometry was pioneered by Guillaume back in 2012 with the seminal paper. And here he used shearing interferometry using this modified Hartmann grating. But because any phase-based measurement also works, you can also do this using off-axis holography. And this is what we did 2 years ago. But you can also push this even further. You can use optical diffraction tomography to actually retrieve these temperature fields. So let me speak a little bit more how this whole thing works. So let's start with the work from a PhD student, Bernard Chirallo. And we basically use the pump probe off-axis holography system. And conceptually, this works as follows. You have your nanosources of heat. So these are gold nanorods that's been embedded on the substrate. And you come with a pump, you optically excite it, and you convert some of that light into heat. And with this, you generate your thermal gradient. Then you come with your probe beam, and you apply wavefront sensing to measure the phase distortion caused by the temperature field. And this looks basically like this if you do a pump on minus a pump off measurement. And so now the interesting part is how do you convert phase into temperature? And again, this problem was solved by Guillaume. There's actually a nice analytical solution for this if you're in the steady state and if you have planar heat sources. And this involves a process of deconvolution followed by a convolution. And this nicely works. You can extract 3D temperature fields with very exquisite detail. How much of an exquisite detail? Well, because this pump probe technique is intrinsically, since we're working with a pump probe technique, this is intrinsically shot noise limited. So we were able to push this almost to the level of 10 to the minus 4 radians in phase. And this is roughly equivalent to getting a temperature sensitivity on the order of tens of millikelvins. And this is a little bit dependent on the deconvolutions, the parameters, and the size of your heat source. But this is roughly a figure of merit that you can reach down to tens of millikelvin. So we got really excited. And so the next thing is like, well, can we resolve temperature dynamics, right? And from a hardware perspective, you can actually, since you have a pump probe system, you can just scan your probe relative to the pump, and you can get time-resolved information. This is very similar to the work that Naomi Ginsberg already presented earlier on in this webinar series. And so the main challenge here was that, okay, from going from phase to temperature, we relied on a model that required the assumption of steady state. And this is where things got complicated because we can no longer use this model. And if we wanted to find another analytical solution, the whole complexity started to add up in terms of computing and doing the temperature retrieval. So when things get very complicated in terms of calculations or simulations, what we do is, well, let's see if we can find a hardware solution. And the hardware solution for that was to switch to a refractive index imaging technique. And this has been exemplified by using optical diffraction tomography. Why did we do this? Because this is intrinsically model-free. And with that, this should mean that we should be compatible to measure non-steady states And we should be able to extend our type of heat sources from 2D to 3D. And the main constraint or the main requirement is that I need to know how my thermo-optical material, in this case water, changes its refractive index as a function of temperature. If I know this value, which in the case of water is really well known, then I can use this as a lookup table to map refractive index into temperature. And this is how I'm going to deliver specificity, especially if I do a pump probe configuration. So how is this implemented experimentally? So you get your quantitative phase imaging method of choice. So in our case, you have your off-axis holography, and you can turn this into an ODT by simply scanning your K vector of illumination. So you basically illuminate your sample at different illumination angles. And you can do this in two different ways. You can modify your illumination path by adding a digital micromirror device, or you can add a rotating wedge prism, as Takuro had showed in a previous webinar. So we went for the easiest solution. So we just copied Takuro's work. So you add a rotating wedge prism, and what you get is the following in your off-axis hologram. And what you see that is rotating is you're basically changing this K vector of illumination, which is represented in this diagram up here. So now that we have all this data, the thing is, what happens next? And so here became the next challenge. Luckily for us, we had this wonderful postdoc called Adarsh, who developed this ODT processing pipeline, and I'll very quickly walk you through it. And if you have more details, you can ask him directly. So the way how this works is that you get your phase images from different angles. From those, you can calculate the scattering wave in Fourier space. You stitch them all together to generate this Ewald sphere. In a way, you can think of this as your 3D scattering spectrum. And the magic happens when you take the inverse Fourier transform, because at this point, this is when you start to get access to this 3D refractive index volume. And once again, if you know how your thermo-optical material behaves as a function of temperature, you can just use this as a lookup table to translate refractive index into temperature. Since this was the very first time we implemented this technique, we were a bit unsure, so we had to make sure to do the proper benchmarking test. So the first point of test was to test whether our ODT system without any heating worked as well. So for this, we used reference materials, so silica beads, put them on a glass, immersed them in PDMS, and we made sure that the refractive index that we measured from those beads was exactly the refractive index stated from them. And this worked quite well. So the next step was to test whether the temperature retrieval was correct. And for this, we relied on simulation. So we used our experimental parameters as inputs, and we verified that there's an excellent agreement between our experiments and our simulation. So now that we were convinced that this approach works, let's test it for some applications. And the first one was to go back to our pump probe, scanning the time delay, and to resolve non-steady state temperature dynamics. So we start again with a single heating source, as I showed earlier in the animation, and let's see how heat diffuses over time. And as you would expect, when you immediately excite this, the heat hasn't had time to diffuse to the system, and so it's actually quite localized. But as time passes, you get the expected 1/r the decay of the temperature field. And as well, you can follow what the temperature is as a function of time. So this is already great. However, Adarsh wasn't satisfied with only working with one beam. So he decided, what happens if you start using multiple beams as well? And so here the motivation was to look at the dynamics of heat propagation, specifically in the aspect and in the context of the time-dependent transition between localized and collective heating regimes. And to illustrate this, he used 5 different heating beams. So this converts in 5 different heat sources. And what you do is to vary the distance between them. And in this tiny little video, you can see how quickly you move from a localized heating regime into a collective heating one. If you put them further apart, this takes a little bit longer, and you still have some aspects of localized heating regime. Again, I'm just showing you 2D images, 2D temperature fields, but intrinsically, this method is 3D. So you can actually make 3D time-resolved thermal landscapes like the following, right? So from that same picture, you can see how heat is dissipating through the environment And so this is actually quite fun. And so now just to finalize, okay, so up to now, we're just working with 2D planar heat sources, so gold particles that have been embedded on the glass interface. So what happens with 3D heat sources? Well, so the first test we did was to embed tiny nanoparticles in a hydrogel and just excite them using our pump ring. And this is very akin to this wide field photothermal imaging that Florian showed earlier, except that rather than resolving the localization of the particles, we're interested in showing the actual temperature fields around each one of these particles. And this is what I'm showing you right here. Because the sample is sparse, you get very localized 3D temperature profiles. But you can also do the system in a dynamic fashion, right? So you can add your gold nanoparticles in water, let them freely diffuse, and you can work at a high enough concentration where you start to get collective heating regime. So now when you come with your pump beam, what you do is you actually induce this collective heating. And you eventually generate this nice diffuse three-dimensional thermal landscape. And finally, to conclude, I've told you that I'm trying to deliver specificity, and the specificity is in the sense is I want to show you that this method gives you temperature only information. And to illustrate this, the best way to do it is to work in a homogeneous, rather messier system. And for this, we picked some cells that have previously internalized gold nanoparticles. And the nice thing about this technique is that since you're doing optical diffraction tomography, you also get label-free imaging for free. So if you look at your pump-off tomograms, you can actually reconstruct the 3D refractive index profile of your sample, in this case represented by these two fixed HeLa cells. And so now the thing that will happen is that if you do this in a pump probe configuration and you excite one of these cells, if you're really truly specific to measuring temperature fields, you would only see temperature originating from that one particular cell. And that is exactly what I'm showing you right here. So I've delivered throughout this collaboration with multiple different techniques a way to measure temperature in 3D. Yeah? And so with that, I kind of want to summarize the results of today. So I've shown you two ways to deliver specificity. One is for the field of label-free sensing. So here's exploiting the use of antibodies to deliver biochemical specificity and to use this as a way to molecular fingerprint heterogeneous populations. And the second option is using pump probe refractive index imaging using ODT to actually measure 3D temperature fields in a time resolved fashion. And with that, I really want to thank everyone that forms part of the Nanophotonic Systems laboratory. There's a lot of people that contributed to this work. I've tried to highlight them in each of these slides. And I want to thank you all for paying attention and listening to my talk. Thank you.
Thank you very much, Jaime. I have to replace Michel. Unfortunately, he dropped out of the Zoom call due to a network outage, and I will continue just sharing, which is an easy task, just to ask for questions for that excellent talk. So who wants to be the first? Except me. So do I see anyone in the chat? No, nobody in the chat. So maybe I can ask quickly. So you emphasized for the tomography for the second part that the key is the knowledge about the refractive index dependence on the temperature of water. So if you deal with heterogeneous systems, like if you have a glass interface or whatever, so how do you have, what needs to be your knowledge about the refractive indices of the individual components, the glass, or the temperature dependence of the refractive index of the glass to really get the temperature map then finally?
So yes, this is correct. So this works quite nicely for most of these scenarios because we're working in aqueous media. So the most of for most cases, this is a kind of homogeneous state. Even when you work with cells, cells are mostly composed of water. So the main thermo-optical material would be water. And you're right. The moment you start introducing interfaces, things can become a little bit challenging. But it turns out if you work particularly in this aspect of having a glass interface on the bottom and water on top, as long as you focus on the areas that are above the water, the whole refractive index reconstruction works quite well. You can actually impose certain conditions such that when you try to retrieve your refractive index, you only consider the areas where this is homogeneous.
Okay.
Yeah.
So how good is that really working also for cells? So typically optical diffraction tomography is heavily used also to get an insight into the objects which are contained in the cell by measuring the refractive index and imaging that three-dimensionally. And now you're adding a perturbation to that refractive index heterogeneity also in a cell. So is the dominant one still the one which you introduce by temperature perturbation, or?
So in this case, yes, you're right. Like there's a lot of things happening with your cell in the cell environment, and in this particular experiment, these cells are fixed. So all the organelles and these things are static. So when we do this pump probe measurement and take the whole tomogram, the only thing that is actually changing is the refractive index environment due to this thing. We actually haven't tried this yet with live cells, just because of this added complexity that you need to make sure that in the time scale that you take the whole tomogram, so pump probe over different angles, nothing else should change in your system other than the temperature response.
So what is the time scale at the end you need for a hologram? Or for...
and well, this I would probably have to ask Adarsh, but I would say this will be in the time scale of around a second. And the reason why this is slow is because we're using a rotating wedge prism. So this is a mechanical translation. So this is much, much slower. But if you look at the recent work of people that are experts in ODT, so you can think of Yong Park, who actually has commercialized this whole optical diffraction tomography, is that they can deliver video frame rate of the tomograms. So they can do this really, really fast. And the way how they do this is they're using DMDs, these digital micromirror devices. So how fast you can acquire these different illumination scans. But yeah, at the moment, this was all very proof of principle. So we worked with slow, static samples where you can do the pump probe, repeated, do time resolved measurements. But yeah, it's true. Once the things are dynamic, this is when the challenge begins, right? And this would be the next time.
Okay, I see. But at least you can do that, would be able in principle to do that also at video rate if you process fast enough.
Exactly. And it becomes a question of signal to noise ratio, right? So if you want to detect small signals, you need to acquire lots of images, and this, the price to pay is time.
Okay. So there are two more questions. The first one is by Dipta Brata. Please go ahead and ask.
Thank you for the talk. So I have two questions. First is, as I understand that the ODT method creates a barrier in the term of the refractive index gradient cannot be too large. So in that case, how large can it be in the methodology that you have developed? And the second question would be, for the time-dependent study, you say that you have a rotating wedge prism which rotates and it takes time, and then you have to focus on each of the k-space points, and in that sense, while it is focusing on the next k-space point, your system has already evolved slightly. And in that case, exactly how does the time dependent measurement work? I was slightly confused about that.
Yeah. So to answer I'll answer the second question because this is the freshest one. So the time dependence, yes, you're right, because as you move, rely on waiting for the next, the wedge prism to move. You assuming that your system hasn't moved spatially, in this case, a cell hasn't moved or it hasn't changed considerably, so that when you take the pump on minus pump off, the only thing that you're measuring is the changes in temperature. Yeah, and all the systems I've shown, the system is in a way static, so that you can go through multiple pump probe cycles, or multiple pump probe cycles combined with the rotating of the wedge prism, that this remains the same, right? So this is a little bit answering back to the question from Cichus. And can you remind me just the first question again?
So the first question was about the refractive index gradient.
Yes. So when you use optical diffraction tomography, yes, there are constraints regarding the refractive index gradient. And so depends on which type of equation you want to solve, right, system. So you can do the Born approximation, you can have the Rydberg approximation, and then there's more complicated ones. For our case, we work in the Rydberg approximation, and I think what's important is that the gradient itself is smaller than I think pi over 2 or something like this. There's a general condition of the Rydberg approximation. But in our case, since we're working with thermometry, so we're working at measuring temperature fields, we're not really worried about the gradients being too steep, because you having this intrinsic 1 over r decay if they are in steady state. And so you have a very smooth very smooth property when you're trying to reconstruct extract the thermal contributions. So this sort of relaxes, allows us to work quite okay with ODT, right?
Okay.
But if you want to work with higher steep gradients, there's a lot of work from people from the computational imaging fields where they can deal with higher steep gradients. But we are not that stage. We're using the very classical Rydberg approximation.
Thank you.
Okay, the second question was by Florian.
Yeah, hey, thank you very much for the exciting talk. It was really good, because I think it would be very helpful to do systematic, temperature, 3D temperature sensing, because we have sometimes the problem to know where does our photothermal signal really come from. And then to see how it develops, maybe also as a function of time. That could be very good. So I have also two questions. One is that you just said that you have a steady state, in a sense that for each pump cycle, you have a kind of the same image or the same temperature distribution. Does that mean that your temperature kind of decays between the pump cycles, or that it is completely steady state, but it cannot be independent of the pump, right? So it has to be always excited for each pump excitation.
Yes, yes, you're correct. So for each pump probe cycle, you have to reset the system to, you have to let it relax. So you heat it, but you also have to wait it to cool down, right? And so again, what you compromise here is that if you have a very kind of huge heat source, it will take much longer to equilibrate. So if you heat it, expose it to, I don't know, you heat it up for 1 second, and to reach steady state, then you have to wait this entire second for let it to cool down, so that you can repeat the next cycle.
Yes. Yeah. But this is the exciting thing, because you can do systematic, investigations of how does it look for different sample and whatever solution or environments. How it does this decay really happen and so on. So that's a very good thing.
And in the end, if you don't follow this nice pump probe cycle, the only thing that happens is that when you measure your phase, you have this juxtaposition of, heating as well as this, while the system is still cooling, right? So it just makes your retrieval a little bit more complicated.
Yeah.
We haven't delved into it too much. So we sacrificed the duty cycle a little bit. And that's why I haven't really stressed the time resolution of how fast you can do it, but rather like, time resolved. Yeah. But yeah, you're correct.
Yeah, and my second question was that now you have measured these temperature profiles and you have excited this with, I guess, with the pumping, but have you related it to certain, species or like compounds in the cell, or did you just in general heat up your sample?
So for all these measurements, we use a certain transduction particle, and these come in the form of plasmonic particles.
Yeah.
So either nanorods, nanoshells, you either coat them on the surface, you let the cells, internalize them, you immobilize them in a hydrogel, or you let them freely diffuse. Yeah. But
okay,
so
the heat is transferred via these particles.
Exactly.
Yeah. But you plan to tune, for example, the pump to certain other, molecular species or something also at some point, or so that you can do without them in any additional particles?
We've thought of it, but I think I think when we first started and back when the group was in Barcelona, it was called the Plasmon Nano Optics.
Yeah.
And so we worked and we had people in our group, that a chemist that, is, almost full-time synthesizing particles with any dimension, shape, and form. So, we had access to all these plasmonic particles that you can tune to any basically to the lasers that we had available in the group.
Yeah.
But yeah, in principle, this should be applicable if you do mid-infrared excitation. If you hit a certain vibrational mode, you can just heat water as well. You come with your 1414 beam. It's in the end, as long as you have a pump probe,
and
you can measure the refractive index, it should be applicable.
Okay, thank you very much. Perfect.